recording. And let me just hide these meeting controls. Great. Awesome. Great. Welcome back to another session of CE 374U Urban Stormwater. Welcome back. It's great to see you. So I've got a couple quick announcements before we get started. We're going to be doing an interactive session in HEC-HMS, if you haven't seen already. But let me go through a couple announcements first before we get started. So first and most importantly, homework 3 is posted. It'll be due next Friday. So not this Friday, but the Friday after this week. And this assignment will be on ArcGIS and HEC-HMS together. So after today, you should have all of the material you need to complete homework 3. But I am giving you 2 weeks because that's approximately how long I think this assignment will take to do, okay? So please make sure you get started early. With homework 2, I just wanted to make a note of this. With homework 2, I got many submissions that were incomplete, which indicates to me that many students did not start early enough. When I give you 2 weeks to do an assignment, that's because the assignment should take about 2 weeks to complete, okay? So homework 3 will be due next Friday at 11:59 p.m. Please get started early. After today, you'll have all the material you need for it. So please also use office hours. Those resources are there for you. So both me and Becky will help you on homework 3. But you need to make sure you get started early so that we can help you, okay? Great. Are there any questions on homework 3 before yes?
You list a bunch of like shape files and data. Do you have like all this filed, or is it
Yes, I do. So data files for homework 3, they are under the announcements. You can find them by going to files, go to GIS, and it'll be homework3data.zip. And that will contain all of the files you'll need for this homework assignment. Okay. Great. Are there any other questions on homework 3 before I get started? Okay, cool. So today, as I mentioned, we'll be doing a in-class tutorial on HEC-HMS. This will be very useful for homework 3. So I'll hopefully be able to answer most of your questions on HEC-HMS today. I have posted a tutorial for what we're going to be covering today under files/activities/HEC-HMS tutorial. So you can find it under Canvas files. If you go to activities and find HEC-HMS tutorial, this will take you through the entire process of what we're doing today, starting with installation and the entire procedure that we'll be following step by step. So if you get lost today, you can always go back and refer to this document. Okay, and Becky and I will also be here to help you as we're going through this in-class tutorial as well. Great. Are there any questions before we go ahead and get started on our module with HEC-HMS? Is anyone having any difficulty installing HEC-HMS? Yes.
They're not on virtual desktop. It's not on virtual desktop.
Okay. There is a Mac version of HEC-HMS.
Yeah, it says it currently can't be downloaded to contact the software.
Okay. So I would just recommend following along with your group members for today, and we will try to figure it out. I feel your pain as a Mac user myself. Okay. But you can find a download link for HEC-HMS. That's weird. My mouse is no longer able to click. That's very odd. Okay, so in any case, you can find the download for HEC-HMS by navigating to the announcements. I've posted announcements with the instructions for finding the download page for HEC-HMS. That should take you to this downloads page here. You'll want to use HEC-HMS 4.10, not the beta version, but version 4.10 for Windows. And go ahead and download and install that if you haven't done so. If you haven't downloaded and installed it yet, you can just do so right now while I'm talking up here, okay? Are there any last questions on getting the software before I move on? Okay, great. Okay, so let's go ahead and open up HEC-HMS. HEC-HMS, we want 4.10. And okay. For some reason, my left clicker is not working on my mouse anymore, and that's going to be bothering me all of today. But I'm just going to have to make do with it. The show must go on. Okay. Great. So HEC-HMS, let me give you a quick overview of HEC-HMS, what it's used for, what you're going to be using it for today. So HEC-HMS is a hydrologic model used for stormwater infrastructure design, used for land use planning, and for hydrologic studies in natural catchments. Okay. So HEC-HMS, the HEC part, HEC stands for Hydrologic Engineering Center. That is a sub-organization within the U.S. Army Corps of Engineers. So this is software developed by the U.S. Army Corps of Engineers. And HMS stands for Hydrologic Modeling System. The first version of this software was released all the way back in 1981. And the first Windows version was first released about in 1998. So the software has been around for a while. It's kind of a legacy piece of software. It is closed source. So only people within the U.S. Army Corps of Engineers can actually view the source code and know what's going on inside of it. However, it's widely used within the stormwater industry for hydrologic modeling. Okay, we're going to be using it as a major part of our class project later on in the course, specifically for the hydrologic modeling aspect. Okay, there are a couple of alternative models to HEC-HMS. I'll just list a couple of them. One is HSPF. You might see this working in industry as well. This is an older model that goes all the way back to the 1960s. SWAT is another competitor to HEC-HMS, but probably the biggest competitor to HEC-HMS today is the EPA stormwater management model. So they, in many ways, are comparable to each other. They are both hydrologic/hydraulic models. So kind of the main difference between SWIM and HEC-HMS, SWIM is typically meant for kind of smaller parcel-based design, whereas HEC-HMS is often used for larger watersheds. And I would say the major difference between them in terms of design philosophy is that HEC-HMS is more focused on the hydrology, so processes such as infiltration, overland flow, and so on, whereas SWIM is more focused on the hydraulics. So in particular, how water moves through sewer pipes. So SWIM was initially developed for modeling of combined sewer overflows. And so SWIM is more sophisticated in terms of how it models the hydraulics. It has a full St. Venant equation solver, and thus it can solve backwater effects and pressurized flow in stormwater pipes. HEC-HMS doesn't have those capabilities. It's mostly unidirectional, mostly models unidirectional flow, but it has additional tools for modeling infiltration processes and other hydrologic processes like evapotranspiration that are often relevant for the hydrology community. Okay, so those are kind of the main differences between HEC-HMS and SWIM. HEC-HMS is used for event-based simulation of watershed runoff and stream flow response. So essentially what we've been talking about for the last couple of weeks, rainfall runoff modeling. It's used for flood modeling. It is used for evaluation of changes in land cover and how that affects the hydrologic response. So for instance, if a new housing development is built, it's often important to know how that's going to affect the stream flow response downstream, and HEC-HMS is often used for that purpose. It's used for simulation of different flood control measures. And finally, it's used for computation of damage frequency curves. So often insurers need to know for a given flood event how much economic damage is expected to occur, and HEC-HMS is often used for that purpose. Okay, so today I'm going to take you through the process of constructing a HEC-HMS model. I'm going to show you the different components of the model, and what you'll need to have in order to have a fully functional HEC-HMS model. I'm going to show you how to specify the parameters needed to run the model, so the hydrologic and hydraulic parameters. I'm going to show you the different kinds of elements in the model, how to connect them together. And at the end, we're going to explore how changing different model parameters, namely the impervious area and land cover, affects the stream flow response downstream. Okay, so we're going to kind of basically in software form do what we've been talking about for the past 2 or 3 weeks. Okay, the full rainfall runoff modeling process. Okay, so let's go ahead. I'm going to go ahead and open up HEC-HMS 4.10 again. Opening it up from the start menu, and you'll get a screen that looks like this. Okay, so this is the HEC-HMS GUI. Okay, we're going to go ahead and create a model. It's just going to be a simple example model of a watershed. The first thing we're going to go do is we're going to go to File, New, and we're going to create a new project. So I will just call this CE 374U in class tutorial. Description, we can enter in any description we want. We're just going to say my first tutorial. Okay, and under location, you can just pick any location on your file system you're comfortable with. For default unit system, we're going to use US customary. So let's go ahead and create. Okay, and you'll get a couple messages that pop up down here. Okay, so now we have a new project. The next thing we need to do is we need to specify all of the components of our hydrologic model. So there's 4 main types of components. You can find them by going up here to the menu, and under components, there will be several different types of components listed. For this lesson, there's 4 basic types of components that you need to know. Okay, the first is the basin model. So this describes essentially the physical layout and physical parameters of your watershed. So that includes things like your watershed land area, your channels or streams, reservoirs, control structures, and that sort of thing. So this is actually your physical model. The second component is the meteorologic model. So this describes mostly how rainfall is simulated, but it also can refer to other meteorologic phenomena like, for instance, evapotranspiration. So this is the part of the model that handles the meteorology. Okay. The third component is the time series data manager. So this is used alongside with the meteorologic model. And in this class today, we're going to use it to specify a rainfall hyetograph. Okay, so this lets you create time series that you can use as inputs to your hydrologic model. And finally, we have the control specifications manager. So this kind of has a weird name. It doesn't actually have anything to do with control as in, control of the water itself, but rather this refers to the parameters of the simulation, such as how long you want the simulation to run and what time step you want to use for the simulation. Okay, so those are the 4 main components. We have basin model, meteorologic model, time series model, and control specifications. The first thing we're going to do is we're going to create a model for our watershed. So we're going to go to Basin Model Manager, and I'm going to go ahead and click on it. And it'll give us this screen here. What I'm going to go do is I'm going to go to New. I'm going to create a new basin model. Let's just leave the name as Basin 1, and I'm going to call it my first basin in the description. It doesn't really matter what you put in this description field. You can put in whatever you want. Okay, so I'm going to go ahead and click Create to create a new basin model. And you see over here on the left that this toolbar shows a new folder which contains our basin model. So I'm going to go ahead over here and I'm going to click on Basin 1. And you note that when we do this, it opens up a new pane that shows a map of our basin. So right now there's nothing on there, but this is going to hold a map of our basin. Okay, and you'll also notice on the top line here in this ribbon, there's a number of different components. So these are the components of your basin model, and I'm just going to go through each of them just so you understand what they all are. Okay, so the first is the subbasin. This is the subbasin creation tool. So this is used to essentially create watersheds. It creates, when you click on subbasin tool and you add it to the map, what you'll essentially do is you'll create a watershed or a land area that receives precipitation input and produces a runoff response. Okay, so that's that first tool over here on the left. The next tool is the reach creation tool. So this essentially creates channels or rivers in your model that you can use to connect different components together. The third tool is the reservoir creation tool. So this allows you to create things like dams or detention ponds, okay, which is especially useful for urban stormwater systems. The fourth component is the junction creation tool. So a junction is essentially just a location in the network where two other elements converge. So for instance, you might have two watersheds feeding into a single junction where all of their flows combine. The next tool is the diversion creation tool. This is essentially the opposite of a junction. So this is when you have flow from one element coming in and it splits into multiple flows coming out. And then finally, you have these two final components, the source creation tool and the sink creation tool. So a source would be some sort of input to your model, like a stream flow input that's flowing into your HEC-HMS model. Whereas the sink is essentially, you can use it as an outlet for your watershed. Okay, and we're going to do that a little later on in class. Okay, so those are the main components of our hydraulic and hydrologic model. What we're going to do is we're going to go ahead and create a watershed by clicking on subbasin creation tool here. And then I'm going to go over to the map and I'm going to click. Okay, and so it's going to ask us to create a new subbasin element. I'm just going to title it My First Watershed. Okay, so a subbasin is essentially a watershed. It's a land surface area that's going to receive precipitation input and produce some runoff response. So let's go ahead and create that subbasin. Okay, so the next thing we have to do is we have to specify parameters for our subbasin. Okay, we're going to specify how the subbasin is going to be modeled physically. So to do that, I go over here to this ribbon. I'm going to click the arrow tool here, and I'm going to go over to the subbasin and click on it. And you'll see over here on the left, I've got a new set of parameters down here that we can specify to model this watershed. Okay, so the first thing I'm going to do is I'm going to specify the land surface area. So this is the land area in square miles. Let's go ahead and just put in 10 square miles for our land area. Now notice this text here is blue. That's because it hasn't been saved yet. If you go ahead and click the save icon here, you'll see that it turns to black, which means that that input has been saved. You can also hit Control S on your keyboard to save, and it will do the same thing. Okay. You'll notice that there's also various other parameters we can enter for our model here. We're not going to be too concerned with most of these. So I'll just give you a quick overview of what they are. Discretization method. So this is if you have a subbasin that you want to divide up into multiple parts. For our lesson today, we're just going to assume it's a single lumped subbasin. So we're not going to use the discretization method. Canopy method, this is used to model plant dynamics. So interception on plants as well as evapotranspiration. Snow method, we're in Austin, so we don't really have to be too concerned with that. Surface method, this is for modeling depression storage. We're also not going to do anything too sophisticated with this. So I'm just going to leave all of them as none. Okay, so we're not going to model any of these components. What we do have to change is these bottom three components here. So the loss method, the transform method, and the base flow method. Okay, so let's take a look at the loss method. What the loss method describes is essentially the model used to compute infiltration. So it's the amount of rainwater that is being lost to infiltration. So if you look through this list, you'll see a couple of familiar friends, such as green amped. So this can use the green amped model to compute the infiltration. What we're going to do is we're going to use our other friend, the SCS curve number, to model the infiltration. So go ahead here and click SCS curve number. It'll ask you about losing data. Just go ahead and click yes. Okay. The transform method, this is the other part of what we talked about the past couple of weeks, which is modeling the runoff over the landscape. So if you see here, there's a various methods that you can use for modeling that process, which I mentioned in previous classes, kinematic wave, for instance. What we're going to use is the SCS unit hydrograph, which you used on your homework previously. Okay, so this is going to be used to model the runoff across the landscape. Okay, and finally, for base flow method, we're not going to be concerned with any kind of base flow entering into the streams from underground. So I'm just going to set this to none. Okay, and make sure you have all three of these set. Did anyone encounter any problems setting those parameters? The area? The base flow method you set to none. So the base flow is essentially representing the flow from the subsurface of the soil to the channel. We're just going to ignore that component.
Why is it like
Because people, hydrologic modelers are often interested in base flow. So base flow is essentially what's going to be creating the stream flow when there's no rainfall input. And so usually there is some sort of stream flow, even though there's no rainfall input. So often it's important to model that. We're ignoring it now because we're just interested in a storm event. So it's not going to be significant. Okay. Are there any other questions on the sub-basin model? Any other questions? Okay, cool. So there's a couple other parameters we need to specify. So we specified the loss method, which describes the infiltration. We specified the transform method, which describes the runoff. We have to go in and enter our parameters for each of those. So first, let's take a look at the loss method. You'll see this tab here next to sub-basin that says loss. Go ahead and click on it. And we're going to enter our SCS curve number. Let's go ahead and just set the curve number as 80. Okay, I'm going to go ahead and hit Control S to save. Okay, so we got a curve number. This is going to inform the infiltration that's produced by the sub-basin. Next, let's take a look at transform. So we can go over to this tab here, transform. We have our SCS unit hydrograph here. So we're using the standard 484 peak rate factor unit hydrograph, which you also use on the homework. We have to specify a lag time. So let's go ahead and just specify a lag time of 60 minutes. Okay, and this is the same lag time that you looked at on the homework. So it specifies essentially the time to peak of the unit hydrograph. Okay. And with that, we are all done with our sub-basin model. So go ahead and pat yourself on the back. Okay. Now that we've created our sub-basin model, the next thing that we are going to do is we are going to go and create a meteorologic model. So go ahead and go to Components, go to Meteorologic Model Manager, and go ahead and click on it. It's going to ask you to create a new meteorologic model. Let's go ahead and click New here. I'll leave the default name as MET1, and I'll call it my first MET model. Let's go ahead and hit Create. All right, and I'm going to go ahead and hit this X here. So now over on the left-hand bar, we now have a set of meteorological models. I'm going to go ahead and click MET1. And you can see here it has a couple parameters. There's one change we need to make. Under basins, in this tab here, we're going to assign this meteorologic model to our Basin 1 model. So let's go underneath Include Subbasins, just select Yes here. Go ahead and hit Control S. All right, and that's all we need to do for the meteorologic model for now. Okay. Are there any questions before I move on? Yes. Yeah, so I clicked on Meteorologic Model, MET1, and then I went to this Basins tab here, and it has an option for Include Subbasins. I just selected Yes. Okay, so we've created our meteorologic model. let's also go ahead here under specified hyetograph. If you go under meteorologic model, we are going to go ahead and select, oh, sorry, we can't do that yet. Sorry, never mind what I just said. Okay, so the next thing we're going to do is we're going to create a rainfall hyetograph. To do that, we're going to go to Components, Time Series Data Manager, right here, and I'm going to go and click on it. It'll ask us to create a new time series. So there's various types of time series you can specify. You can specify precipitation. You can specify other kinds of meteorologic inputs like humidity, wind speed, air pressure, but we're just going to be interested in precipitation. So I'm going to go ahead and click New. It's asking us to create a gauge and ask a description. So I'm just going to say my first rain gauge is the description. Okay, let's go ahead and hit create. And it created a new icon here over on the left for time series data. Let's go ahead and expand that. And we have a set of precipitation gauges here. Let's go ahead and click on gauge 1. And we're going to make a couple of changes here. So we're working in US units. So what I'm going to do is I'm going to leave data source as manual entry, but for units, this is important because it will change the output if you don't change this. Set, instead of incremental millimeters, select incremental inches. So just like the alternating block method, we're going to use a hyetograph in incremental inches. Okay. And for time interval, we're going to change it from 15 minutes to 1 hour. I'm going to go ahead and hit save. Okay. So underneath gauge, now you can see that there's an expandable menu. I'm going to go ahead and hit this expandable menu. And there will be this icon here that says, it gives you a set of dates. So this is describing our hyetograph for this gauge. I'm going to make a few changes in here too. So right now it has a start date of January 1st, 2000. I'm going to update this a little bit to January 1st, 2022. And for the end date, I'm going to change it to January 2nd, 2022. Okay, so this defines the start and end time of your rainfall hyetograph. Okay, I'm going to go ahead and hit Control S. Okay, so now what we're going to do is we're going to specify the rainfall hyetograph for our rain gauge that is going to serve as the input to our model. So let's go ahead and I'm going to change it up. This is going to diverge a little bit from the notes, but I'm going to go ahead and crowdsource a rainfall time series from you. So let's decide on a rainfall time series collectively. So you can't specify the inches of precipitation for the first hour. You start with hour 1, so you can't specify it for hour 0. But for hour 1, we can enter our first precipitation value. So what's a good first precipitation value? Let's keep it under 1 inch. Let's keep each one under 1 inch. We don't want it to get 0.4. Okay, cool. Okay, next one. 1. Let's do 0.25. Okay. Okay, next one. 0.7. I heard of 0.7. Okay. Next. 0.3. Wow. Okay. Next. 1. Let's try it. Okay. And for the 6th hour, this will be our final one. What's a final rainfall value? 0.1. Okay. So this is all over the place. This looks like Texas weather. Yeah, for sure. So there's one final step we need to do. We need to fill in the rest of these with zeros, or else the model will not run. So I'm going to go and fill in the rest of these rows with zeros. Okay. And we have our rainfall hyetograph here. I'm going to go ahead and hit Control S to save. And it goes and saves all of those. We can visualize the rainfall hyetograph by going over to this tab here that says Graph. And you can see our rainfall hyetograph here. Very interesting pattern. So I'm excited to see what it looks like when we run it through our hydrologic model. Okay, great. So we've got our hyetograph. Now we have to do one more thing before we move on. We have to go back to this icon here that says specified hyetograph underneath our meteorologic model. See this icon here? And for gauge for subbasin 1, we need to assign gauge 1 to subbasin 1.
I have a quick question.
Yes.
Just about the saving the new font. Do you have to do that like after every change, or say 3 changes and then say that it's still save the original 2?
So you don't need to save after every change you make. In fact, if you switch to another tab, it'll automatically save it. I'm just doing it to be safe here. Yeah. Okay, so we're almost done. We're almost done with our first watershed model. We have our basin model, we have our meteorologic model, and we have our time series data input. The last component we need is the control specification. So this essentially describes how long the simulation is going to run and at what time step it's going to report results. Okay, so let's go ahead under components and click on control specifications manager. It's going to ask us to create a new one. So I will say create a new control specification descriptions, my first control specifications. Great. Let me go ahead and click create. And I will exit out of here. On the left, we now have this tab with our control specifications. Okay, I'm going to go ahead and click on control 1. And it's going to ask us for a start date, an end date, a start time, and an end time. So I'm going to make these commensurate with our hyetograph. So for the start date, I'm going to put January 1st, so 01 Jan 2022. Our start time is 00:00, so that would be midnight of January 1st. Our end date is going to be 002 January 2022. And our end time is going to be midnight, which is 00:00. For the time interval, I'm going to leave it as 15 minutes. Okay. And with that, we have all 4 components of our hydrologic model created. Okay. So what we're going to do now is we're going to create a simulation run. So let's go ahead and go up here. And underneath the ribbon, under compute, we're going to go to create compute and then go to simulation run. And we're going to go ahead and click simulation run. Okay, so it's going to ask for the name of our simulation run. I'm just going to leave it as run 1. It's going to ask for your basin model. So we're going to select basin model 1. Okay, note that this refers to the entire basin model and not just the sub-basin. So we're going to select basin 1. For our meteorologic model, we're going to select MET 1. And for our control specification, we're going to select control 1. Okay, and with that, we can go ahead and finish. Okay. And I heard an error sound. Oh, it's a battery sound. Are there any power strips you can use? There's a couple around here, so let's just figure out a way to make sure you get a power outlet. Can we move this one up in front a little bit? Okay, or you can just set up in the front as well. Okay. Okay. Great. So we've created a simulation run. To access our simulation run, you'll see that there's 3 tabs here: components, compute, and results. We're going to go to this compute tab right here in the middle. Okay, and you'll see there is a folder for simulation runs. If you expand that folder, you'll see run 1. Okay, so this is the moment of truth. We are going to go and try to run our simulation model. Now, I want to preface this. Version 4.10 of HEC-HMS is a bit buggy. So when you try to run it, sometimes it will not successfully run. If that happens, I'm going to close the program and open it back up. And it will hopefully run. I've done this 4 times now, and it works every single time. Okay. So
I have that issue. I was running through it because I have found that issue.
yeah, so version 4.10 is very buggy. I'm not exactly sure why this is the case, but I will, that's probably what I'll end up doing. Yes, you have a question?
So this is a border design. Is that-
Yeah, so there are several reasons that could occur. It's possible for it to occur when there are no problems. If that happens, you close the program and reopen it. Okay, so let's do this moment of truth. I'm going to right click on run 1 and I'm going to hit compute. And there it is. So if it does not go to 100%, that means that the run was aborted. So what I'm going to do is I'm going to go ahead and close. I'm going to exit out of the program. I'm going to reopen the program. Okay, I'm going to open up our project. I'm going to go to compute, simulation runs, run 1, and I'm going to hit compute. And there you go. Don't ask me why. This only happens with version 4.10. So I think in future versions of the class, I'm just going to skip this version of HEC-HMS and try a different one. Okay, so note that we have completed our simulation run. Right now, I'm going to go through the class and just check on you to see what issues you're having. But first, before I do that, I want to give you a way to verify whether it ran correctly or not. Okay, so you'll see there should essentially be, if there's any warnings or notes that are not in black text here, that's an indication that your model may be incorrect. But we can check the results by going to this results tab here, over here. And under simulation runs, we go to run 1. And there's a couple different features here I just want to take you through. There's a global summary table. This lists global summary information such as the peak discharge, the volume of runoff, and so on. And there is also a graph that we can access. So if we go to subbasin 1 and then go to graph, it'll give us a graph of the hydrograph coming off of the watershed. Okay, so if your model run completed successfully, you should be able to access this graph of the model run. Okay, so this is the outflow from the subbasin in cubic feet per second. I'm going to go around now and just check and see if any of you have any issues that you're running into. If you have any issues, please just raise your hand and I'll come help you out. But you should be able to find this plot of the output of the model underneath the results tab in HEC-HMS. Okay, so is anyone having any problems with their model? Okay, great. Let me go. All right, cool. If I could have everybody's attention, please. Hello, everybody. Oh, thank you. Thank you for your attention. So it looks like everyone was successfully able to get the runoff response modeled for a watershed. So let's go ahead and just go through some of these outputs here so we can interpret them. If we go to the results and we go to subbasin 1 and click on the graph, this will give us a graph of the runoff response for our subbasin. I just wanted to go and show you the individual components of this graph. So on the bottom, we have the flow coming off of the watershed in cubic feet per second. So this would be similar to the flow produced in homework problem 2.2, where you're computing the flow coming off of the watershed. So this is the runoff response in cubic feet per second. This top part here is the rainfall hyetograph, but it's partitioned into the total precipitation and the amount of precipitation that infiltrates. Okay, so the red the red component of this hyetograph is the component of the precipitation that infiltrates, and the blue is the excess precipitation, essentially. So everything that doesn't infiltrate. So you can see, what part of your rainfall infiltrates and what part becomes runoff. Okay. Great. Are there any questions so far on the modeling of a watershed in HEC-HMS? Any questions? Yes. You will be doing that on homework 3. Yes. You'll go through the whole process of delineating watershed and creating a HEC-HMS model out of it. Okay, so this is good. I just wanted to show you a couple other things. So we showed the global summary. There's also a summary table for our individual subbasin. So this gives you things like the peak discharge, discharge volume, and so on. And we also have a time series table. So you can use this if you want to copy and paste output into Excel, for instance. So this is a time series of the runoff and infiltration within subbasin 1. Okay, so that's great. We modeled the runoff response to a single subbasin. Most real world hydrologic models, though, will be a bit more complicated than this. Okay, so if you go back to components and you open up your basin model, okay, we only have a single subbasin here. So this basically, what we've modeled is just the runoff response within a single watershed. But in real world hydrologic modeling, you'll often have multiple watersheds that are connected together by channels or reaches. Okay, so what we're going to do in the next part of the class and for the remainder of the class is I'm going to show you how we can construct a hydrologic model that has multiple subbasins and where flow is routed between those subbasins using a reach. Okay, so we have one subbasin here. This is also something that's going to be on homework 3. So just make sure you know how to do this process. Okay, so we have one subbasin here. Let's go ahead and create another subbasin. I'm going to create another subbasin with the same exact parameters as the first one. So under subbasin creation tool, I'm going to click on subbasin creation tool. I'm going to go over here to the map and I'm going to click to add another subbasin. I'll just leave the name as subbasin 2 and I will omit the description. Okay, and I want this subbasin to have the exact same parameters as subbasin 1. So I'm going to click on subbasin 2. For the area, I'm going to give it an area of 10 square miles. For loss method, we're going to choose SCS curve number again. For the transform method, we're going to select SCS unit hydrograph again. And for the base flow method, we select none again. Okay, so it's the exact same as the first subbasin. For the loss, I'm also going to give it a curve number of 80%. Sorry, not 80%, a curve number of 80. And for the transform, I'm going to give it a lag time of 60 minutes, just like the other subbasin. Okay, so we've created 2 subbasins. Let's create a junction to join the flows from these 2 subbasins together. Okay, so underneath this ribbon here, I'm going to go to junction creation tool. It's this one right here with the 2 things going into one thing. I'm going to click junction creation tool and I'm going to add it to the map right here. I'll leave the name as junction 1. And this is a nice element because there's no parameters to specify. So we'll just leave it like that. Are there any questions on this process so far? Any issues you're running into? Okay, we're all good. Okay, the next thing I'm going to do is I'm going to create a sink. Okay, so this is essentially going to represent the outlet of our multi-watershed system. So I'm going to go ahead and in the ribbon here, I'm going to select sink creation tool. And I'm going to put a sink down here kind of at the south end. And I'll leave the name as sink 1. Okay. And I do not believe there are any parameters to specify for the sink. So we'll just leave it like that. Okay. Now what we're going to do is we're going to connect junction 1 to our sink using an open channel. So I'm going to create a reach Up here in the ribbon, we have this reach creation tool. So this will represent basically a segment of river or channel that's going to connect junction 1 to sink 1. So I'm going to go ahead and select the reach creation tool. I'm going to go over to the map and I'm going to draw it here. We'll leave the name as reach 1. Okay. And over here on the left, I'm going to select reach 1. So for this one, we are going to change around some of the parameters. So just pay attention as I populate these fields, but the instructions are also in the document if you get lost, okay? So for the routing method, we're going to select kinematic wave. So this is the same kinematic wave we talked about earlier in the course. Did you have a question?
Yes, I have a little trouble drawing my reach. Is there a trick to it?
You click once, release the button, move to another location and click again. Yeah. So I clicked just in the blank space. I didn't click on any of the other elements. Yeah. Okay. So for routing method, we're going to select kinematic wave for the reach. I'll just give you a second to catch up. Okay, for routing method, we're going to select kinematic wave. And then under the routing tab, we're going to populate these parameters. So just follow along here. For the length, we're going to make our channel 6,000 feet. For the slope, I'm going to give it a slope of 0.0004. For the Manning's roughness, I'm going to give it a roughness of 0.013. The subreaches I'm going to leave as 2. And so for these parameters, just follow along here. For the index method, I'm going to select celerity. I will tell you a little bit about what this means in a second. For the index celerity, I'm going to put in 5 feet per second. For the shape, I'm going to make the shape a rectangular channel. And for the width, I'm going to give it a width of 10 feet. Okay, so most of these parameters are self-explanatory except for the index method and index celerity. Essentially, these are used for determining the discretization of this element. So it's kind of a computational concern. The celerity refers to the wave speed, and it has to do with how the element is discretized when it's solved numerically. Okay, so that's what that parameter refers to. You don't have to worry about it for the purposes of this class. It's just a numerical concern. Okay, great. Are there any issues with creating the reach? Okay, so note that a reach, this represents a segment of open channel, a river, or a conduit. Okay, so it's used to represent flow in an open channel, essentially. Okay, there's one more step we're going to do. And that is we have to connect up all these components. So I placed all of these components on the map, but right now they are not connected to one another. So in the final step, we are going to connect them all together, and then we are going to run the simulation again. Okay, so for subbasin 1, for each of these, we're going to specify the element that is downstream of that element. So you notice here, if you click on subbasin 1 over here on the left, there will be a field here for downstream. This is the element that is downstream of that element. So for subbasin 1, I'm going to select junction 1, and this will connect subbasin, sorry, I changed it to sink 1 for some reason, junction 1. Okay. So if I go ahead and hit the save button, it'll connect those two elements together. Okay. So for subbasin 1, select junction 1 as the downstream element. For subbasin 2, we're also going to select junction 1 as the downstream element. So I've clicked on subbasin 2 here. For the downstream element, I'm going to select junction 1. Junction 1, let's try it again. And I'm going to go ahead and hit save, and that will connect them together. Okay, so for junction 1, we're going to set the downstream element as reach 1. So the junction is going to feed into our reach. So I'm going to select reach 1 here as the downstream element for junction 1. And for reach 1, I'm going to select the downstream element as the sink. Okay, so I'm going to select sink 1 as the downstream element for reach 1. And with, yes,
The channels between subbasin one and junction one have the same properties as the breach between junction one and sink one?
so there is no channel between subbasin one and junction one. This is just connecting subbasin one directly to that junction. So there's no channel in between them. Subbasin one will feed directly into junction one with no channel transition between. You can basically think of it as subbasin one, the outlet of subbasin one is directly connected to that junction. So there's no channel with a length for it to flow through. Yeah. Good question. Thank you. Okay. And with that, we have all of our components connected together. There's one last part we have to do. We have to go back and under specified hyetograph, we have to connect subbasin 2 to gauge 1. So we have to give subbasin 2 a rainfall input. So that is the last step. And with that, we should be able to simulate the response. So let's go ahead and go to compute. I'm going to cross my fingers. I'm going to go to the compute tab here. I'm going to go to run one, and let's go ahead and hit compute. Oh no. Okay, let's go ahead and save, and I'm going to exit the program. And I'm going to open up HEC-HMS 4.10. Okay. We're going to go back to CE 374U in class tutorial. I'm going to go to compute. Let me open up the Basin model again. I'm going to go to compute, simulation runs, run one, and hit compute, and there we go. Okay. So note it gave a couple of warning messages this time. These are just warnings. So the program ran successfully. It's just giving you a couple of warnings that we can talk about. But with that, we successfully ran our subbasin, our multi-subbasin model. If we go to results over here in this tab here, we can look at our simulation run. So let's go to run one. If we go to global summary, you'll see that now we have 5 different elements that are in our global summary. We have subbasin 1, 2, junction 1, reach 1, sink 1. They all have their own peak discharge associated with them. We can also go and look at the ultimate output of this basin model by going to sink 1. This is the outlet of our model. Let's go to sink 1 and let's look at the graph. Okay. And we got a nice hydrograph here with a peak of about 5,500 cubic feet per second. Okay, so this is adding up the contributions of both of those subbasins, routing them through a channel, and then looking at the output at the outlet of this model. Okay, so I'm going to just use this time right now to go around and just check. Is anyone having any issues with their model? Okay, great. I'll give you about 5 or so minutes to plug me down if you have a question. All right. So there's one last thing we're going to do. This is a kind of a group activity. So if I could get your attention, please. Okay, thank you. So there's one last thing we're going to do today. We're going to look at how the watershed responds. We're going to look at how our watershed model responds to changing the parameters of the watershed model. Okay, specifically what I'm going to have you do is in your groups, you are going to change the parameters of your subbasin model corresponding to your project group number. And you're going to go ahead and simulate the model again. And I want you to record the peak flow produced by your model, as well as the time to peak in minutes. And I'm going to have you come up here, and for your group number, I'm going to have you write down the peak flow from your model, as well as the time to peak. Okay, so I've created a spreadsheet here. So for each group number, I want you to go back to your subbasin models, and I want you to change the curve number and the impervious percent based on your group number. So for both subbasins, go and change the curve number corresponding to your group number shown here. And I want you to re-simulate the model and record the peak flow rate and the time to peak. So did you have a question, Colin? So let me, I prepared for this scenario. So I have the project groups up in the announcements. Yeah, so these are your group numbers here. So I will slowly scroll through them just so you can get them right now, but it's up in the announcements if you want it, okay? Okay. So is everyone clear on what you're supposed to do? Okay, I'll answer you in a second. I'm gonna go and write the group numbers up on the board. I'm gonna write the fields for the peak flow rate and a field for the time to peak in minutes. And once you go ahead and simulate your model with your curve number and impervious percent, I want you to go up and write it on the board underneath your group number, okay? Okay, I'm gonna go do that and then I will answer your question. To this one, yes. All right, so if I can get your attention, please, for one last thing. So we're almost done, and it looks like everyone was successfully able to run their HEC-HMS models. So this is essentially the same process you'll be doing on homework 3. Homework 3 will be taking you through the process of creating a model based on GIS data. So it's going to be a combination of ArcGIS plus HEC-HMS, a very useful skill to learn, which you will be doing in industry. But I wanted to just draw your attention to the results. So we varied the curve number of our watershed from about 70 to 98. And you can see that just varying that curve number from 70 to 100 resulted in almost a threefold increase in the discharge at the outlet. Okay, so just kind of a take-home lesson in how much land cover can affect the results of your hydrologic model and how much it can affect the runoff response for real-world watersheds. Okay, so are there any last questions on HEC-HMS before I let you go for today? Any? I guess that's a no. All right. Great. Well, I will see you on Thursday. Thank you.